Good to go.
Okay. I'm pleased to introduce Dr. Lavanya Raman for today's talk. She got her PhD from IIT Madras in metallurgical and material engineering. And she moved to Penn State very recently in 2022. And in her PhD, she was working on mechanical behavior of refractory high entropy alloy. And she has been continuing her work at Penn State as a postdoc. Today, she will talk more about the high entropy alloy and how they can be applied in different high temperature applications. Lavanya, whenever you are ready to go, please.
Thank you. Yeah, sorry about that.
Is someone else in the room with their audio on with you?
No, I think now it's fine, right? Yeah.
Yep,
So
it's good
you.
now.
Yeah, so thank you so much for introducing me. So most of you know me, the work that I have done. So yeah, so I'll start sharing my screen. I hope now the slides are in the presentation mode and it's visible. Okay. Yeah, so good morning and thank you everyone for taking time to attend this talk. So the title of today's talk is refractory high entropy alloys, which can be a potential high temperature material. So the outline of the talk goes like this. So I've planned what do we mean by high temperature materials, what are their characteristics, and why we need or how we can come up with new materials, and why at all this refractory HEAS and how we can classify them, and what is the role of the alloying elements which will help us in developing a good refractory alloy which will meet the application requirements. And finally, the main part will focus on the work which has been done extensively on this composition, which is chrome, moly, niobium, titanium, tungsten in equiatomic proportion. We'll see how we made this alloy from different routes and stage by stage. What is a microstructure? Is it really thermally stable, and the deformation behavior? So finally, some learnings that we have from the work which has been done and how we can extend or go ahead. So coming to the high temperature materials, so all of us know that the efficiency of any working system can be improved when the material can operate at a higher temperature. So this is the famous equation. So all of us know. So when the operating temperature of a material is higher, the efficiency can be increased. So when we say the material has to operate at very high temperature, so it has to have a very high melting point and it should have certain characteristics. So we will see what are those, what will make a material qualified as a high temperature structural material. So first and foremost important thing is that, so when you take any material or an alloy, so when you heat it to a higher temperature and then apply load, so it should have creep resistance. That is, it should not change its shape and size. So that is the foremost thing, which should have a very good creep resistance. And then comes a stable microstructure. So the grain size or the faces, it should be really stable. And then depending on the atmosphere in which the material will be used, so it should have adequate oxidation and corrosion resistance. Also, the material should not be so heavy. So when we say for structural application, if the material itself is heavy, so it will be very difficult to handle. So it should have optimum density. And another important qualification is it should have adequate room temperature ductility so that we can avoid catastrophic failures. And then comes our high temperature strength. So since we are designing a material for high temperature, so we need strength which can be retained at those high temperatures. So keeping all these things in mind, we can now address why we need refractory HEAS. So this figure here shows the temperature capability of different materials across different temperature scales. So if we look in closely, like above 1000 Kelvin, so we have superalloys, some refractory metals, and titanium aluminum alloys. So one thing to note is that so all these alloys are mainly based on one major element. So we call that as a one principal element. So in superalloys, we have nickel base, cobalt base, and iron base. So when we say TiAl alloys, so it can be either 50-50 composition or it can be a multi-phase intermetallic alloy. And in terms of refractory alloys, we have tungsten heavy alloys or like a niobium C103, so which is based on one major component. So now when we look at this diagram, so the questions that arise in our mind are like how we can improve the performance of these existing materials, or like what can be done, maybe like say fine tune or like have some composite or like kind of ODS addition so that you can improve its durability, strength, and performance, or like how efficiently we can design these alloys. So when we have these questions in our mind, so we thought we'll go about how we can efficiently design these alloys. So the birth of HEAs happened like in 2004. So wherein people like mixed different elements together. So it can vary from 5 to 35 atomic percentage, so that you have a combination of elements so that the synergy of each element will give you a better performance. So when we say refractory high entropy alloys, so these elements are like definitely like refractory in nature. So wherein their melting point is greater than 1500. So when we like mix them together, so in desired proportions, so we can make HEAs. So one advantage or like very unique property of these HEAs are like they have very high melting point and they can retain their strength at high temperatures. So however, they have very few applications because of this following point. So they are like highly dense, like tungsten is almost like 13 gram per cc, and they don't have the optimum ductility at room temperature. Also, they can easily form volatile and porous oxides. And it's extensively like difficult to make a high pure alloy or even metal. So these are the properties of these refractory HEAs. So now in the refractory HEA community, like there are like so many alloys which have been developed so far. So I have tried to classify these alloys based on the density so that it will be easier for us to identify the domain which we want. So the first and foremost alloys developed in this field was like tungsten containing, which was mainly like moly, niobium, tantalum, tungsten. So with some vanadium addition, and then there were some modifications. The main intention of this study was to make alloys which can retain the strength at temperatures above 1200. So in the study, they have showed like up to 1500, like it can retain the strength. So, but the major drawback is they are like highly dense. So the density is very high. And then they modified the composition. So wherein they added like hafnium, niobium, and zirconium. So this was mainly developed to have a combination of strength and ductility. And they like were found to be like having a single phase, so which was really good. And moving ahead, so people try to add aluminum to the refractory alloys, although we know aluminum doesn't have that high melting point. So the main intention to add aluminum was to reduce the density and to have better oxidation resistance. So this aluminum containing alloys, so they had a B2BCC microstructure, which is similar to the superalloys, which is like a basket weave microstructure. So they showed like optimum density, strength, and ductility. So this was like a really good way of making alloys, which satisfies most of the criteria. And finally, to further reduce the density of the alloy, people added like chromium, titanium, and vanadium. So when the addition of chromium and vanadium happened, like it led to the formation of Lavanya phase. So this, although it increased the strength, so there was a drawback in terms of the ductility. So these alloys were like very brittle. So now, so I have summarized like what all lessons we can learn from this HEA field is that, so tungsten containing alloys, they are highly dense, they lack room temperature ductility, but good point is they have this high temperature strength retention. So in the second class of alloys, they have adequate room temperature ductility, but the major drawback is the thermal stability. So they tend to form precipitates or some intermetallic phase upon long heat treatments. And finally, when we added chromium or vanadium, so they reduced the density, but the formation of lavage phase made the alloy very brittle. And in case of aluminum, so we containing alloys, so we have a good combination of density, ductility, and strength, but the major drawback is thermal stability. So also, like I've tried to summarize like how we can choose elements depending on the role of each alloying element. So as we can see, when we have aluminum, it can give better oxidation resistance, or it can promote B2 structure, basically a BCC phase. But in this case, it results in an ordered BCC phase. So when we have chromium and vanadium, so we can expect lavage phase to form when it combines with elements like niobium and titanium. And these elements, hafnium, zirconium, and titanium, which are like HCP at room temperature. So when we have these elements, so it tends to give adequate ductility at room temperature. Mainly moly and tungsten we need when we are aiming for those temperatures which are above 1300. So they help in retaining their strength, and they have very good wear resistance. So finally, when we need to have an alloy with adequate ductility and toughness, so we'll have to add elements like niobium and tantalum. And some studies have shown that addition of vanadium and titanium helps in refining the grain size. So these are the things which we can get from the literature. So now we'll have to design an alloy which will have an optimum combination of everything in terms of density, ductility, strength, and thermal stability. So for that, before going into that, so I've tried to have one slide which will help us understand the gap in the literature. So if we focus on this figure, so this shows the variation of compressive yield strength across different temperature scales for different materials. So this has mostly like different refractory HEAs. Also, like they have shown superalloys like Inconel, Haynes, and MA-WM. So if we look closely at first glance, so one may think that these superalloys, they drastically reduce their strength as we go temperatures above 1000. Whereas these refractory alloys, like they show a kind of a steady state region where the strength is retained. But when we look in closely, in both the cases, the strength drop happens at around 0.6 of Tm. The only advantage what we have in these refractory alloys is, so their melting temperature is very high. So because of that, we will have access to those high temperature domains which we cannot achieve using these superalloys. So only because of the melting point of these refractory HEAs, so we can go to temperatures above, let's say, like 1300 Kelvin. And another important thing is in the literature, most of the studies has been done on the cast HEAs. So we don't know how these alloys will behave if we make them through powder metallurgy route or any other metastable synthesis route. So how those microstructures will be, or like how the different processing routes can affect the microstructure, and will they be really thermally stable, and what are its deformation mechanisms. So these are the three things which we have tried to focus in our work, and this is where like the literature also like lacks more study. So for to addressing those questions, so we have chosen this composition, which is like chrome, moly, niobium, titanium, and tungsten. So the rationale for choosing this composition can be understood from this figure. So this figure shows a work which is done by Christopher Schu's group for binary tungsten alloys. So wherein they have showed that these nanocrystalline binary tungsten alloys can be really stable at around like say 1100 degrees. So depending on the choice of second element. So the region here in green contains elements like chromium and titanium, majorly which are close to the boundary. So what happens is that when we add elements from this stable region, so they tend to segregate at the grain boundary, making the grain boundary stable. So it paints the grain boundary so that it cannot grow even at such high temperatures. So from this, so we have chosen chromium and titanium. So we just want to see when we extend from the binary to a multi-component system, so whether this idea will be applicable or not. So that was the reason why we chose chromium and titanium, just to stabilize the nanocrystallinity of the alloy. And from the previous slides, like from our learnings from literature, so we have chosen like niobium, which we need to have sufficient ductility, and also like moly and tungsten, so we need for high temperature strength. So this is why like we came up with this composition. And this alloy we have tried to make through two different routes. One is like vacuum arc melting, the conventional one, so that we can compare with the literature. Another like non-equilibrium synthesis route is a powder metallurgy, so wherein we use mechanical alloying. So in that we try to synthesize the alloy using wet milling condition. So when I say wet milling, so we use a process control agent, toluene, so that the powders are immersed in that when we make the alloy. And in dry milling, so we don't use any PCA. So in the dry milling, we varied the atmosphere in which we make these powders. So one was done in air, and another was done in an inert argon atmosphere. So we have tried to characterize the alloys in their as synthesized condition. And the experimentally observed phase formation was validated through the CALPHAD studies, and we also saw the thermal stability. And finally, the deformation behavior of the cast alloy and the wet milled alloy has been studied. So I'll be showing these things in detail. So to start with, for the mechanically alloyed wet milled condition, so we used Fritsch high energy ball mill, where these individual elemental powders were added in equiatomic proportion. So the ball milling was done at 300 RPM with toluene as the PCA in tungsten carbide vials. So once we have the powders, when we characterize them using XRD, it showed the formation of 2 BCC and some residual elements. So we also try to estimate if we have any contamination from the toluene or the milling media. So then we found we have this much amount of carbon. So after we sinter them at 1300, so we have this kind of a microstructure, so where you can see different contrasts. So with the help of EDS, so we were able to identify these phases. So on total, we have 3 BCC phase, titanium carbide, and Cr2Nb lavase phase as the secondary phase. So these in the 3 BCC phase, the lattice parameter is like very close that we couldn't resolve them. So when we tried the EBST to get the grain size, so all these 3 BCC phase are indexed as 1 BCC. And we tried to validate the experimentally observed phase formation using CALPHAD. So for that, the composition of the sintered sample was given as input along with the carbon content that we measured, so that we wanted to see if we can predict the TIC formation as well. So now, since our sintering temperature is 1300, so if we see at that temperature, so we have TIC and BCC, so which is like almost close to the experimentally observed phase. So this CALPHAD couldn't predict Cr2Nb because that is because of the experimental conditions that we have. So here we have some residual elements which is not reflected in the calculations. So otherwise, we can say that the CALPHAD predicts the major BCC phase and the possible secondary phase that we can have. So which is like really good. So coming to the dry milled condition, so we made these alloys using a similar treated high energy ball mill. So here the milling media was like hardened steel vials and balls. So this is a horizontal high energy ball mill. So as I mentioned, so we varied the milling atmosphere. We carried out in air and argon. So here is the XRD pattern, so which shows us what are the phases that we have. So when we mill them in the powder state, we have a BCC phase and the residual chromium and niobium. So like how we had in the wet milling scenario. But when we sintered these alloys, so we have different kinds of secondary phase depending on the milling atmosphere. So this is the microstructure of the alloy which was milled in air. So what happens is when we milled in air, so the residual elements chromium and niobium, So they reacted in a different way. So when, as I mentioned, the milling media here is like hardened steel vials and balls. So from these milling media, we had some amount of ion contamination. So the residual chromium reacted with this ion. So this has very strong affinity, and it formed a sigma phase, which is an intermetallic phase. So whereas the niobium combined with titanium, and it formed secondary carbide. And since we carried out this in the air atmosphere, so as we know, among these elements, titanium has more affinity for oxygen, and it formed TiO2. So basically, we have a BCC major phase with sigma, titanium oxide, and a multi-carbide as the secondary phase. So now, when we carried out it in the synthesis in argon atmosphere, so we have different kinds of phase formation. So these residual elements, they combined together to form a Cr2Nb Lavage phase. So, and we may think like, why not in this case chromium couldn't react with iron and it formed a sigma phase? Because when we did it in argon atmosphere, we reduced the milling time, and it didn't have it had only like half the ion contamination. So it's not like sufficient enough to form a sigma phase. So also like the oxygen content in this scenario was very less. So rather than TiO2, we had a titanium oxynitride phase, and we had like two BCC phases. So one is like tungsten rich, and the other one which has a multi-component in nature. So in the dry milling scenario, depending on the milling atmosphere, so we have two different kinds of secondary phase. So summing up the last slide on this one, so we can see that when we try to make these alloys through powder metallurgy route, so they are like very sensitive to your milling conditions or atmosphere and the milling media. So they decide your what secondary phase you can expect. So when the same composition we made using arc melting, so we obtained a single phase BCC. So this is the SEM microstructure, wherein we can see that elements segregate into the dendritic and interdendritic region according to their melting point. So here like tungsten has the highest melting point, so that goes into the dendrites. And then moly and niobium, they go to the interdendritic region, and the last to solidify will be chromium and titanium. So the single phase nature of this alloy is confirmed using EBST. And when we did the CALPHAD studies, this also shows that at high temperature, we have only a single phase BCC. So now to summarize the phase formation of the microstructural variation of this composition when we make through different alloys. So we can see that casting route gives a single phase BCC, whereas the powder metallurgy route, depending on either it is wet milling or dry milling, and also the milling atmosphere and the media, we have different secondary phases. So one thing what we learn is the extent of alloying which happens in the powder metallurgy route decides your secondary phase, and the way in which you make these alloys, like that the milling atmosphere and the milling media, so that results, that also like helps you in identifying what secondary phase you can have. So the table here shows some studies apart from this work from the literature, so wherein people have reported similar phase formation for this composition. So now that we have made this alloy, so we have to really establish whether these alloys are thermally stable before we can actually study its properties. So for that, we tried to understand the structural stability at 1300 for 10 days. So we vacuum sealed these samples in a quartz tube and did a heat treatment for a long time. So from this XRD pattern, we can see that only the phases which were present in the as synthesized conditions are retained, and we did not observe any new phase formation. And also like from the EBSD analysis, we estimated the grain size. So this the structural stability here is shown. When we say thermal stability, we have to make sure that the alloys are like doesn't they have proper grain growth resistance. So for that, we try to calculate this growth factor, so which is nothing but the ratio of final grain size upon initial grain size. So when I say like final grain size for the powder metallurgy route, it is the grain size of the alloy after heat treatment. The initial grain size is the as sintered grain size. So this we normalized with our temperature and time, and this is the homologous scale. So we have compared the alloys that we made with the alloys in the literature. So we can see that they have the least growth factor, which means they are really stable at 1300 for a sufficiently longer duration. So this helps us in establishing the structural stability. So now we know that this alloy has different kinds of phases and this is really stable. So now we have to understand the deformation mechanism of this alloy. So for that, for the mechanically alloyed composition, we did this compression studies using Glebel, which is a thermomechanical simulator. So we did compression test and the temperature range of 1000 and 1350 at different strain rates. And after the completion of the test, all the samples were quenched immediately in water so as to retain the deformed microstructure. So these are the stress strain graphs. So at 10⁻³ strain rate, we can see that at all test temperatures, the alloy showed a 50% compression ductility. One important thing to note is that at lower temperatures, so the alloy has a peak hardening followed by softening, whereas at high temperature, it shows a steady state behavior. So at higher temperatures, when we deform them at different strain rates, that is like when you deform it in a very slow manner, or if you deform it very fast, the alloy behaves in a different way. So at higher strain rates, it shows a peak hardening followed by softening. So which means that initially up to a certain strain, so the alloy work hardened. So we'll have to apply more and more force to deform the alloy. So whereas once you cross certain amount of barrier, so it is easy for the to deform the alloy. Whereas when we do at a very slow strain rate, the material has enough time to rearrange the dislocations inside it, and it exhibits a steady state behavior. So from this stress strain behavior, so we can see that there is a peak stress followed by the softening. So this kind of behavior is an indication for this dynamic recrystallization to happen. So just from these graphs, we may not be able to say that for sure. So what we have to do is to check the deformed microstructures. So before that, from these stress strain graphs, we can establish the deformation parameters such as the stress exponent and activation energy. So conventionally, these deformation parameters are calculated for the flow stress at a particular strain. So generally, if we do that at 1% strain, so we have a stress exponent of 3 and an activation energy of something close to 500. But here we have seen that the material is very sensitive to the way we deform, whether it is in a fast or in a slow way. So the material is very sensitive to the strain rates. So what we tried to do was calculate these parameters as a function of strain and strain rate. So when we did that, we can see that the stress exponent, it varies with increase in the plastic strain. So it decreases up to a certain level and then it increases. Whereas the activation energy in low strain rate conditions, it's almost stable, but at higher strain rate condition, it goes to a peak and then decreases. So this clearly tells us that the flow stress is a strong function of your deformation temperature, strain rate, and strain. So this is a classic behavior of any BCC alloy. But important thing to note is that the behavior, how these parameters vary can be understood from the stress strain graphs itself. So it may not be correct for us to establish these parameters if we follow the conventional way. So we'll have to examine the deformed microstructure at each stage to understand what exactly is happening. So overall, from the stress exponent of 3, what we can say is that some dislocation based activity is the deformation mechanism happening in this alloy, but we'll have to confirm that only when we examine the deformed microstructure. So in another, so the deformed microstructure looks like this, wherein we have some localized deformation bands. So this localized deformation happens when the alloy is not able to take that much amount of strain in one go. So this is a kind of instability behavior. So we will understand why this is happening in the later stages. So when we look into these bands closely, so I have showed the SEM microstructures here separately for the inside band and the outside band region. We can say that all the faces have deformed, but the extent of deformation of these faces are more in the inside band region. So that is, these bands take up more of a strain compared to the other region. So now to understand this dynamic recrystallization or the softening mechanism, so we did EBSD analysis. So we have tried to index the BCC and titanium carbide phase. Using the grain orientation spread, so we can calculate what is the recrystallized fraction. So as we can see, the recrystallized fraction of the BCC phase, they increase with increasing strain rate and it decreases with the temperature. So from this EBSD pattern, it is clear that at the interface of BCC and titanium carbide, so we have very fine recrystallized grains. And also when we combine this GOS analysis with the secondary phases that we have, and also with the high stacking fault energy of this HEA, so we can confirm that. So what's happening in this alloy is like a continuous dynamic recrystallization. So that is one thing which we'll have to understand. So it's not like a conventional, like non-continuous dynamic recrystallization. The presence of secondary phase and the orientation gradient within the each BCC grain, so that results in this CDRX. So now to understand the flow localization, so we did some intermittent strain tests. That is, we stopped test at a particular strain and then quenched the sample to check the microstructure. So like that, we conducted tests at different strain levels. So when we checked these microstructures, we were able to identify the flow localization only at 30% of plastic strain. So which means the flow localization happens somewhere between 0.2 to 0.3 of the two strain. So in the literature, people have showed that usually this flow localization or the shear banding that happens beyond 25% of strain. And also what we observed from the dynamic recrystallization study is that DRX occurs at strains way below, way ahead of this flow localization. So which means DRX happens first, followed by flow localization. So that is what is DRX is what is causing the flow localization in this alloy system. So now to confirm the deformation mechanism, so we did some TEM analysis where we could see that inside the BCC grain, we have glide of 1/1 dislocations, so which confirms the dislocation glide to be the active mechanism in the mechanically alloyed and sintered HEAs. So now coming to the cast HEA, so the flow curve of the cast HEA at low strain rate is shown in this figure. So where we can see that they have very high strength compared to our mechanical alloyed counterpart. And the deformed microstructure of the alloy at 1200 is something like this. So where we can see the precipitation of this lavage phase in the interdendritic regions. So this lavage phase confirmed to be CR, NB and titanium rich through the elemental mapping analysis. So the as-cast alloy in the synthesized condition had only like single phase BCC. Now after deformation, we have the formation of lavage phase. So to understand the deformation mechanism, so we took a TEM lamella from this region, so where we have a BCC, this lavage phase, and some titanium rich regions. So as you can see, the titanium rich regions showed some twin formation, and there were like a lot of dislocations and subgrain formation in the BCC phase. So the formation of subgrain is an indication of dynamic recovery happening. So in the cast alloys, we have dynamic recovery as one of the mechanisms. And also like we could see a lot of dislocations in the BCC phase. So from this dislocation imaging, so we try to understand what is the strength contribution coming from the dislocation. So that is like, if we go by this equation, so sigma y gives us the overall yield strength, and the contribution from different sources can be the solid solution strengthening, which can come from a single phase BCC, and the grain size strengthening depending on the grain size of the alloy, the precipitation strengthening, which can be from this Laves phase, and the dislocation strengthening from the dislocations that we observe in the BCC phase. So when we try to quantify the individual contributions, so we can see that when we add up the grain size, precipitation, and the dislocation strengthening, so it comes to only like 200 MPa. But whereas the experimental yield strength at this 1200 degree deformed condition was like 600 MPa. So this clearly shows us that the dominant contribution comes from the solid solution strengthening. So which means for the cast alloy, the solid solution strengthening is what is resulting in the high strength. So now to compare the behavior of these alloys with other HEAs, I have tried to plot the yield strength variation. So as we can see, the cast alloy is on par with the other cast alloys. So whereas this mechanically alloyed and sintered alloy has a very high strength at 0.5 of homologous, but it decreases as we go to high temperature. But we can say that this composition, when we make it through arc melting, it is on par with the literature. So to summarize, the takeaways from this talk is that, so this composition, when we try to synthesize through different routes, it really shows how the processing route can affect your microstructure. And also like we can validate our experimentally observed phases with the CALPHAD, which is a unique tool which will give insight about the plausible secondary phase formation. And also the alloy has an excellent thermal stability, wherein no new phase was formed. And in the deformation behavior of this alloy, the MA-SPS alloy showed a dynamic recrystallization and flow localization as a softening mechanism. Whereas in the cast HEA, so we have solid solution strengthening as the major strengthening factor, and dynamic recovery as the mechanism. So this is so far like what we have done majorly on one composition. So here current work focuses on using this machine learning to design these alloys. So wherein we give all the information from literature to the database, and we use certain models to design alloys depending on the application. That is like what should be your yield strength or the creep resistance, like what we want, depending on those data. So the deep learning and the CALPHAD high throughput calculations will give us these compositions, which will be made using vacuum arc melting or fast process, and then the properties will be studied. So this is a way wherein we can use this computation or any simulations to reduce the amount of experiments that has to be done. So which is a really a good initiative, so that we can come up with new compositions depending on their requirements. So yeah. So thank you all for listening. So please like let me know like if you have questions. I'll be happy to take them. Okay.
Hello, can you hear me?
Yep.
Yeah, it's a very nice presentation. I have one question towards the last slide, the strengthening contribution that you shared. So
This one?
Yeah, the one, yeah, here. So did you calculate really the dislocation density to find the dislocation strengthening contribution?
Yes.
So did you do that from the TM or from EBSD or some XRD experiment?
No, from the TM. Like these are the two images which I have showed, but I had to take multiple images where have more number of dislocations. So you can calculate the dislocation length in a given area and calculate the dislocation density.
So you had to take into account the film thickness, like the TM.
Yeah, Zamla thickness. Yeah.
Okay. And
Lavanya, you got really quiet.
I'm sorry.
your volume got really quiet.
Just a second.
Yeah, could you repeat that once more? I could not hear properly.
Okay, I'm sorry for that. So basically, from the TEM image shown in the last two figures, so I was able to calculate the dislocation length, the number of dislocations in a given area. So from multiple images, I calculated the dislocation density, and using this formula, like we can get the strength from the dislocation.
So how about if the dislocations are really tangled, like on the right-hand side images, like the length? Yeah.
So like,
how do you estimate that?
So more or less, like I took the linear length. So when like we are measuring like more dislocations, so it's an approximate contribution. So that's why we have the standard deviation as well.
Okay. Yeah, I mean, just wondering, because I think studies are also done on a routine basis for some. I don't know how good are they for the dislocation density.
Yeah, so that is a good question. So from the XRD, we can estimate, but when we have this multiple phases, it may be like very difficult for us to identify from BCC, that is the major phase, what is the contribution coming up. So the XRD is always a bulk technique, right? So
yeah, that's true.
Yeah, yeah. So that's why like I had to go for this TEM to get how the BCC phase is affecting or contributing to the overall strength.
So the second thing is, how are you sure it will be a linear additive rule for the strengthening? Because is it a very standard thing for, I'm not sure about high entropy alloys, but for other alloys like aluminum alloys, it's not always a linear addition rule for the strengthening contribution.
True, like we for these HEs, we never know whether the linear addition or the rule of mixtures will work or not. We don't have any other equation as of now. So this is one better way to understand how each factor is contributing. I'm not saying this is the only way or the best way, like how we can estimate. So this is one of the ways which will give us an overall picture.
Okay, and so you did not actually calculate the solid solution strengthening, right? It was just taken as a difference of the expected strength and the.
Yeah, we did calculate the solid solution strengthening, but I did not cover it in the PPT. Maybe like you can check this manuscript, so that will help us more.
Okay, so you take into account the amount of solid solution available and then the contribution of each of the elements?
Yes, like, so the contribution of the composition of each elements and how the individual physical property, as in the shear modulus or the Poisson's ratio, how it affects. So all those things.
How much is available in solid solution? How do you take that into account? Because you might have given an initial composition, but only so much is only available as solid solution. How do you find that?
Yeah, just a second. I'll see like if I can share that screen. Just 1 second. So it's like what we do is that the solid solution strengthening of this alloy is basically a variation of temperature and these parameters. So it's not, we cannot really like quantify or have one model. Yeah, so just a second. So as you can see in this figure, so we tried to estimate, this is only for the solid solution, so how the dislocation interacts with the BCC element. So as you can see, there is a wide range. So we cannot really say how much comes from the solid solution exactly. So from the equation, we can understand like more than 50% is the contribution from solid solutioning. But depending on your Poisson's ratio and shear modulus, it varies, like it has a very wide range, because for these alloys, so it is very difficult to estimate the experimental Poisson's ratio and the shear modulus. So what we did in our study was to use the shear modulus and the Poisson's ratio from different sources, like basically from the established database or from the materials project. And the Poisson's ratio we tried to estimate from the synchrotron studies. So when we use different sources, we could see that the solid solution strengthening, it is very sensitive to these parameters. So if you see for this one, the mu-L, which from the materials project, so we when we take the lower value of the shear modulus, so it shows that the yield strength is very less. So, but when we go with the values from the Ashby-Frost deformation handbook, so it shows that it has a very high yield strength. So this is something which we really need to work on, and a lot of people in this community are working on this solid solution strengthening model itself. So using DFT and correlating that with experiment. So it's kind of tricky because we never know what could be the dislocation nature, whether it is edge or screw. So there's a lot of things to play with.
Yeah, that's what I wanted to. So do you have this available in that paper that you just showed, like this?
Yeah. So yeah, okay, it is there in the manuscript. Yeah.
Yeah. Thank you. Thank you for your answer.
Thank you.
Any more questions for Lavanya?
Can I ask one question?
Yes, definitely.
Please.
Yeah, very nice presentation. So as you mentioned, this kind of systems has several challenges at high temperature. If I understand correctly, about 1300 degrees Celsius and above, maybe that range. So of course, we are using this metallic element, which most of the metal are ductile in nature. But when you make alloy, then you say some grain boundaries or some cracks start happening. So some key points which is very challenging, which in this area of research people are always very concerned. If you can briefly give a light on it, it will be very helpful.
Okay. So one main challenge is, first of all, identifying one particular research application. So overall, when we say refractories, it has high strength. So, but we also should know how each and every element atomic percentage should be, or like what elements we have to choose. So the alloy design is kind of challenging. So that is where now people are using this high throughput calculations, or what to say, not just completely rely on the experiments.
Machine learning or kind of things.
Yeah, machine learning kind of things. So it's like we cannot completely replace superalloys. Superalloys has been like used like more than 50-60 years, and the work done on that is very extensive. So we may have to apply the learnings from superalloys or like those well established structural materials to this alloy system, so that we can know what combination of phases we need to have. So definitely if we just go with a solid solution, we cannot meet all the requirements. So we may need to have some carbide addition or Lavage phase, like in superalloys we have Lavage strengthening from MC or like M2C kind of carbides. So there are a lot of factors. So something like that needs to happen here. And another main challenge is their high temperature testing. So there are like very few places where we can actually do like tensile test of these alloys. So in literature, most of the data is on the compression. So the compression testing doesn't reveal a true picture of any alloy. So that is where like we have major challenge.
Thank you very much. It's very informative. Yeah.
Thank you
so much.
I have one more question on the identification of the phases that you showed, the different B2 BCC phases. So you said the EPSD could only identify one type of the BCC phase, right?
Oh, yeah.
But you, I think somehow you mentioned there were 3 kinds. So how did you do that? Was that from the EDS or was that from the TM?
No, that is from the SEM, like BAC and EDS analysis.
So it was some localized, like areas,
just a second.
Point EDS stuff?
Yes, point EDS. So basically this is the SEM BAC image. So where you can see different kind of contrast. So from this different contrast, I can get the composition. So when I say this is like BCC2, BCC1 is the gray matrix-like thing which has all the elements. So this white region is the BCC2, which is like tungsten rich. So depending on the composition from the EDS analysis, we can identify we have 3 BCC.
So BCC1 is rich in one of the, like, which major alloying element?
No, this has everything. It's just titanium depleted, because the titanium goes as a secondary phase in titanium carbide.
And what about BCC3? Like, I know all of them has everything, but there must be.
I mean, the variation is BCC3 is slightly moly rich. So this is one of the bottleneck in when we do mechanical alloying. So we have to compromise on the contamination as well as the extent of alloying. So
okay, So BCC3 is also titanium rich. What did you say? Actually, I missed that.
This is moly rich.
Moly rich.
Yeah.
And is this present like in homogeneously throughout, or is it just? I mean,
it is homogeneously present. So the A figure is the low mag image. You can see the different phases are like homogeneously distributed.
Okay. Yeah. Thank you.
Thanks.
Okay, if no more question, let's thank Lavanya again for excellent presentation. So I think we can stop recording now.